Film capture?
Yeah. Yeah, you can. You made it.
Or HDMI.
Sure. HDMI. Actually, it has a converter. HDMI Type-C converter here. Yeah, you don't need your converter. It has own. Oh, but sure. You can use that.
Either way.
Yeah,
Yeah.
way. Yeah. And,
It's just becoming a lot more common now, right? So you want me to
yeah, where the mic?
wear that?
Yeah,
Okay.
Let me know when you're ready. I can. Let me know when you're ready.
Just give me a quick second, just so I can set my timer. So whenever you're ready.
Okay.
Yeah.
Hello, good morning, everyone. Welcome back to MAE seminar series. So it's my honor to introduce Professor Erik Thostenson, currently a distinguished professor in the Department of Mechanical Engineering at the University of Delaware, with a joint appointment in the Department of Material Science and Engineering. He's a leading researcher in the field of composite materials, specializing in carbon nanotube and advanced fiber reinforcement. He currently leads Air Force Research Lab program, focusing on low-cost, high-performance composites for attributable structures. He is a recipient of prestigious awards, including NSF Career and Young Investigator Program from the Air Force Office of Science and Scientific Research. He is also he received the Elsevier Young Composite Researcher Award from the American Society of Composites. Please join me in welcoming Professor Erik Thostenson to our department seminar.
So thank you very much. It's certainly an honor and a pleasure for me to be here today. I've visited campus a number of times before, but never gave a talk in this department. So what I'd like to do is share, kind of some of my work over the past, for almost 20 years now. I've been involved with research on processing, characterization, and modeling of carbon nanotubes in their composites, specifically nanostructured materials. And what I want to share is some of our very recent results, looking at the ability, some of the novel ability of these materials, where we can add a nanoscale reinforcement, and we can add some new functionality to an existing material system. And I always like to start with this slide. I call it my signature slide. Almost every presentation because I think this really highlights. So what you see here, on the left, this is carbon fibers, and as I mentioned, I've been working in composite materials for a long time. So advanced fiber reinforcements, typically embedded in a polymer matrix. So what this is a carbon fiber. This is a carbon fabric. You can see the woven structure. On this is an individual carbon filament. It's about 7 micron in diameter, so about the 10th of the diameter of a human hair. And on that, we've grown the carbon nanotubes directly onto the fibers. So this was some work I did is almost over 20 years ago now, actually, as a PhD student. But this motivated me over the past 20 years to look at how we can combine these reinforcement scales. So when we talk about composites, typically we're talking about advanced fibers embedded in polymer. I like to call this a multi-scale hybrid composite because we're really combining different reinforcement scales. Oh, okay. So having a little challenge with the so here, just a quick overview of my talk. I'll talk a little bit about the scalability and particularly not only multi-scale, where we talk about micro and nano up to macro, and highlight some work in using these as sensors, specifically carbon nanotube-based sensors. I'll talk about the manufacturing approach that we use, and really what this has been the enabling technology is that we developed a process that's very scalable, and now we can make materials that have, it's very scalable, and we can manufacture these at ambient temperatures, which has really opened the door to a lot of kind of unique collaborations. And then I'll talk about some work that we've been doing in structural health monitoring, specifically to rehabilitate and monitor structures. And then also some of this work, I call it from structural health to human health, where we've been integrating some of these sensors in clothing. And I've been collaborating with some of my biomechanics colleagues at looking at taking the kinematics and kinetics of human motion and being able to monitor that at a large or over time. And I think one of the things, especially years ago, we talked about this issue of manufacturing and nanomaterials and the scalable, so this bottom-up manufacturing where we're going to assemble these materials. But to me, that this was something. Okay, to me, this was something that was very natural, having worked in composites for many years before I even started my PhD, is that composite materials are really bottom up, or we truly design them at varying lengths of scale. And really, as an engineer, that's what intrigued me, is that we design them from both the micro and nano scale all the way up to the macroscopic part. So for composites, if we look at the different levels of scale, we have the fiber and the interface, and we can tailor that interface, and that's certainly at the nanometer scale. We have, we can bend and weave these fibers together, something NC State is very well known for in textiles, all the way up to the ply level, and finally, the final net shape composite. So this was something that we've been doing, an engineering approach that we've studied for years in composite materials. And one of the unique things, and is really what's enabled a lot of my research over the past 10 years, is that these carbon nanotubes are conducting. And if we create networks of carbon nanotubes, what dominates the electrical conductivity, we can add just a small amount and make something electrically conductive. But what dominates the conductivity is not the conductivity of the reinforcement. It's actually that contact resistance or quantum tunneling resistance. So a lot of things can happen. So if you stretch it or heat it or whatever it might be, is that this region where you have the electron tunneling, that contact resistance changes and enables this sensing. And this is what we call material that's called piezoresistive. And piezoresistive means it's if you have a strain gauge or something, if you stretch something that's a conductor, what the change in electrical conductivity that you measure is this change in the length and then also the Poisson contraction. But in this case, what we do is that when we stretch it, these tunneling gaps, even though that resistance change might be very small at that level, we're adding it up over thousands and thousands of individual contacts. So this is really the mechanism. As we stretch it, these tunneling gaps change, and then actually what can happen is if you get a crack, that permanently severs the conducting network. And when we first published this work, it drew a lot of attention, and I think it's a very practical application of nanotechnology. Nanotechnology is often abstract, but it's very practical application. In order to sense a microscale crack, you see this is a very small crack, but we see these individual conducting carbon nanotubes protruding into the crack. In order to sense a microscale crack, you need a nanoscale wire. Okay. Today I'm going to talk about some of our very recent work and structural health monitoring, but this is really what I was just talking about is, we've done a lot of different things in terms of sensing of damage in joints and detecting microcracks in fiber composites. And also, but today I'm going to talk a little bit about the structural monitoring and repair of fatigue cracks in steel bridges. And then also these textile sensors for monitoring physical rehabilitation. And that's really, I'm a material scientist by trade. Not working. So I'm a material scientist, but now I've been collaborating with colleagues in civil engineering and biomedical engineering. So I'll first talk about this scalable manufacturing approach, and this has been really the enabling technology. And we studied this science in the lab, and now we're scaling it to a roll-to-roll type of process. So instead of making a few square inches, we can now make yards of this material. And as I mentioned, I'll talk about this interdisciplinary collaborations where we've been using these for in situ sensing. And, again, I showed this slide before, but this is just a sort of, I think the key challenge and the opportunity is that we can combine the reinforcement scales together. And when I first did this, we were using chemical vapor deposition, so a very high temperature process, over 600 degrees C. And so very few fibers are going to survive that process. You really need either a ceramic or even some carbon fibers will start to degrade. But I was intrigued by this. So what we started doing was looking at this process that is ambient temperatures and called electrophoretic deposition. And it's something that we can industrially scale. We can study it in the lab and study the chemistry. We can control the chemistry. So what we do is we take the nanostructures. We use mostly carbon nanotubes, but we can disperse a lot of different particles like graphene, and we disperse them in water. And then we have chemically functionalized them. And the chemical functionality we use, we've studied a lot of different, but we use what's called polyethylene amine. And when we lower the pH, the amine groups protonate. And that does a couple of things. It stabilizes the dispersion. These tend to like to stick together, so the positive charge repels each other, but that gives us mobility. And we can use an electric field to deposit. And we can use both direct current and alternating current. But on the right-hand side, what you see, this is a cross-section of a fiber, and when we deposit, it's not really just like the tubes are raining down onto the fibers or the fabric, but it actually coats it gives us a very, very uniform fiber level coating. It's almost like a sponge. That's what you see in this texture up in here. Those are the carbon nanotubes, and the chemistry sticks, it bonds to the surface of the fiber, both for different chemistries, but it bonds to the surface of the fiber, but the nanotubes also, because they also react together. So we have a very, very uniform and well-bonded structure on the surface of the coating. And so this is just kind of, quick highlight is that we have a lot of control over the nanotube purity and functionality. We're doing this at ambient temperatures. So instead of just, carbon and glass fibers, we can now deposit on a wide range of natural and synthetic fibers and organic fibers. And that's really been the enabling technologies. So what's interesting with this process is that we back it with an electrode. This is the chemistry that we're using. We chose this for composite materials, but it's been an interesting process. So we can modify the shear strength, or basically the bond strength between the layers, and also the interface. This is some work we did almost over 10 years ago now, but we've really expanded this to look at the microscale interface. And so what we're seeing is a very significant increase in that strength just by this chemical functionality. And we're not adding a lot of material. We're adding, just a few milligrams of the material onto a fairly large piece of fabric. And we've done a lot of studies. This is something that is actually just under submission, where we've looked at modifying the interface. And here you can see there's significant stiffening. You can see the indentation depth as we move from across that epoxy nanotube interface. Significantly, we're changing those properties at the very micro scale, but we can, and that affects the macro scale properties. This is also where we did some nano scratch, and you see the indentations or the scratches in the epoxy. And you can see this of the nanotube epoxy. You see the significant amount of debris is we're significantly increasing the fracture toughness in that area. And then I think what's really unique about this is, as I mentioned, the tubes don't just rain down onto the surface, but they deposit on the back electrode. So if we have a substrate electrode, the carbon nanotubes want to actually get to that electrode. And of course, what happens is we get electrolysis of water. It's like the high school experiment where you split oxygen and hydrogen, right? So that electrolysis changes the pH, and then that causes the tubes to precipitate out. And so what happens is, because it's electrically conductive, it grows as an extension of this electrode. And we've studied a lot of the kinetics of that deposition. And this is just an example where we wanted to show that this is not just raining down. So we did some work where we had a perforated electrode, and you see initially that pattern shows up on the fabric, but at longer times, that network starts to grow as an extension of the electrode. And this is just where we wanted to show the mechanism and visualize this at a larger scale. Here we have rods that are maybe a millimeter or two, and we did the same deposition, and you see that coating starting to grow. And again, what you see here also is that coating growing initially on what's in contact with the electrode, but then over the surface. And that's what gives us this really uniform coating. We can also do, we can control the process quite a bit as well by using what we call AC, or asymmetric ACEPD, is that we can actually control and we can limit the amount of electrolysis by having a zero net integral of our wave. But because it's nonlinear, it moves a little more in one direction. So it moves a lot under the high voltage because of the electrophoretic mobility, and then under the lower voltage, it doesn't move back as much. So we get this net movement in the mobility, and we spend a lot of time. I mentioned we've studied the deposition kinetics. It depends on a lot of different things. What our electrode is, what our concentration is in the dispersion, and what our electric field is. But it's something where we can often just deposit in just a few minutes and get a very uniform coating onto the fibers. This is where we've been doing it for longer because we want to get more material in there to increase the mechanical properties, but we don't have to add much for electrical properties. So what you see here, just a couple of minutes You see these bright rings. This is a gallium ion microscope image. So the bright rings are conducting area. So where we don't have anything deposited, this is a glass fabric, I believe, you don't see anything. But you see over very quickly, you see this, this conducting network form. And that's what enables our work in sensing. This is also shows some morphology under ACEPD, and for ACEPD, I mentioned, is where we want to get more material in. So this is where we've deposited it. But you see these large regions of conducting materials. So that's just a highlight. We can control the morphology a lot by controlling the process and developing our process window. And then this is just an example, as I mentioned, for the AC and DC, is that for the AC, that nonlinear mobility gives us a net deposition. And we can control that thickness of that coating, and that's like this sponge-like coating. And so you see here it's maybe a couple hundred nanometers thick. Here, this is less than 200 nanometers. So again, it's really a fiber level coating, and we can coat not just high performance fibers, but now we can coat things like cotton or wool or polyester. And you see the wool fiber has this kind of cuticle structure, and we have this uniform coating still on that as well. And we can also have a lot of control over tailoring the electrical conductivity. So these are just under different conditions of deposition, looking at how we're changing the electrical properties, both in plane and through thickness of a fiber composite. And this electrical conductivity tailoring, it's not that we're necessarily looking to control the electrical conductivity, but that is what gives us that ability to do piezoresistive sensing. And this is also something that we've looked at as quite scalable, is that, you know, as I mentioned, it's something we can do in the lab, and we make a couple of square inches of material. But we've now had this capability where we can scale it up as a roll-to-roll process. And so this is, you know, again, a batch process versus a continuous process. Here we have our fibers. They can go through a deposition bath. We've developed a small pilot line in my lab, and it's partly because there's so much interest in the sensing work, everybody wants some of the material. So I get calls from companies asking for it, and I'm like, well, we can make a couple square inches for you, but they want yards. So we developed this pilot line. One of my PhD students created a startup company, and we built this pilot line in my lab. It was actually paid for by the startup company, where we do this continuous deposition. And we have a rolling or a moving electrode. And then there are several different steps. What you don't see here is the furnace for drying. But again, now we can coat individual fibers, we can coat fiber bundles, we can coat fabric. And we can do it in a very uniform way. So this is where, as I want to spend about the last 25 minutes or so talking about where this is, for me, opened up a lot of interdisciplinary collaborations. As I mentioned, my background is in processing and characterization and modeling of nanocomposites, but we've started and we've expanded where I collaborate in civil infrastructure and also in biomedical engineering. So I'll just mention, so there's kind of three topics. I just want to mention some of our work. We have a Department of Energy project looking at using electrical impedance tomography to not only have, you know, instead of having a sensor that where you measure something locally, where we can actually map something. And that's something is, say, if you had a composite and then you have local damage, you know, composite planes, there's a lot of them, they get struck by birds, right? So you can get delamination. And so this is what we want to do, is localize, not only that there's damage, but we want to localize that damage. And then I'll talk about a unique project where we took an idea from, from the lab, where it was just an idea, we validated it in the lab, and we actually put a sensor on a bridge, a couple of bridges, actually one in Wilmington, Delaware, and also one in Portland, Oregon. So this what I mentioned is a spatial sensing using electrical impedance tomography, and we've done a lot of different things where we might introduce damage, but we can also apply a pressure. And what we're doing is that we inject a current around the boundary. This is one of the sensors. This is a fairly small one, just a few square inches. But we inject a current and we measure boundary electrodes, and then we use a finite element program to solve for the conductivity distribution. And this is opened up where, and again, this is some of our flexible sensors. This is where we've done some pressure mapping. You can see these localized regions. What's happening is we're compressing the composite in that area. And by that compression, that changes the electrical conductivity. So we're backing out that conductivity map. Of course, if you have damage, so if there's, let's say, impact damage in a composite, we can detect that too. And not only can we do that, but we can detect the extent of damage. This is just another kind of interesting example where we were using this in composites manufacturing. And in composites manufacturing, we do processes where we do what's called an infusion mold. We take a liquid resin and then we infuse it through a fiber preform. And in this case also, we can measure that as well, is that we can measure the position of that flow, and our current Department of Energy project is looking at utilizing this for the liquid molding and doing this sensing in real time, so that if a defect is forming, say there was a dry spot, here we're injecting from the edge, and you see our conductivity map. If there was a dry spot to form, we could change the flow or try to force that into a different direction. And this is just, again, I'm just showing this kind of spatial damage mapping. So we've used this for sensing. And then this is what I'll talk about next is that utilizing composites for structural rehabilitation, but also sensing. And this is just an example. This is a what we call a compact tension specimen. It's pretty large, actually. It's about a foot square. And in fact, I joke with my civil engineering colleague that this is the largest test specimen I ever tested. And it's the smallest one he ever tested. So, so here, what we're doing, this is compact tension. We're driving a fatigue crack, and we have a sensor on there to monitor that crack. But also what we want to do is look at not only the crack growth as a part of a sensor, but where we could add a composite onto the surface. And that composite, when we bond it to the surface, shares the load in the structure. And we can slow the fatigue crack. So this was a multi-year project, as I mentioned. It was funded by the Federal Highway Administration, where we took it just from the idea that we talked to some of our colleagues at the Delaware Department of Transportation, and there was a lot of, especially in the 90s, there was a lot of research using composite materials to rehabilitate infrastructure. And of course, infrastructure is deterioration of infrastructure is even more of an issue today. And the DelDOT engineers were like, yeah, this is great. They saw some very nice results where they didn't have to replace the structure, but they could rehabilitate it, bring it back up to its original load condition. They said, all this is great, but you covered up the damage. We can't go and inspect it. So our idea was that, well, we could use these sensors that we developed in the lab to monitor the growth of damage and underneath a composite repair. As I mentioned, one of the things is that, and of course this one is by far now the largest beam. What we have here, this is actually a 16-foot beam in the structural our civil structures lab. And what you see is instrumented on this side. This is a composite repair and also a sensor. On this side, we just have a couple of sensors, and these are what are called a shear wrap or a U-wrap that goes around the beam. So these are fairly large sensors, and it really is a distributed sensor. As I mentioned, it's for EIT, we can get a lot of information. And if cracks form, in fact, in this part of the beam, it has deficient shear reinforcement. So that's why we're doing this rehabilitation, but we've also now integrated the sensing. So if the cracks grow, they'll extend further. Okay, so again, steel, this is just an example of steel bridge deterioration. We can get corrosion, I've now, when I've been collaborating, I know that a lot of our bridges have a lot of fatigue cracks, a lot of them. And in fact, this is a fatigue crack in a girder that is not too far away from campus. And this goes over interstate highway. And what they've done here is they've they drilled these, what's called a crack stop hole. So that blunts the crack tip. So that reduces the stress concentration of the crack. Yeah. But one of the things you can see here, this crack was growing and the first crack stop hole didn't work. So they drilled another one. And for fracture critical bridges, they actually replaced this whole bridge recently. But these fracture critical bridges are a major challenge. And this is also where you see corrosion. We could bond a composite and design a composite system that would, we can clean the corrosion off, but also rehabilitate that girder. So our idea was to integrate both the repair as well as monitoring. And what you see in this picture actually is our compact tension specimen, and where we've integrated a structural composite patch to share some of the stress or some of the load and take that stress off of the crack. And this is a micrograph and a little cartoon showing where we've integrated the sensor right at the bond between the structural reinforcement and the steel plate. So we've added our structural reinforcement, and we can, because our sensor is very thin, we can slip it in that range. And this is just showing as the crack grows, even though the composite is not cracking, that crack will still grow under the composite. But we've designed the strain to failure of this sensor such that it fragments as that crack grows. So we have this, what we call our sensing skin that's integrated at the bond between the composite and the steel. So these are just some different configurations. Of course, upper right-hand corner, that's where we drilled a traditional crack stop hole. And then on the bottom, that's where we've integrated a structural patch, structural repair, but also integrated a sensor. And this is where we've also, in addition to integrating it, we've drilled a crack stop hole. So hopefully this video works. There we go. So this shows the sensor in action. So we're just starting the initial test. But you can see the sensor is integrated into the patch. And you can see that we're measuring, and we can measure that. And we're fatiguing it, but we can sense that fatigue damage or fatigue in real time. And then over time, as that crack grows, we see the sensor fragment, and we can very actually monitor that. Of course, we study this in the lab and have also done a lot of modeling of the crack. This is a finite element, extended finite element simulation, but we've also done digital image correlation, and you can see the stress concentration at the crack tip. And I like these videos. This is if we have no fatigue crack, and of course you see that high stress concentration at the crack tip. And this is our simulated part where we use that simulation to design our repair. This is just an example of now the stress that's in the composite with the composite repair. And you can see as that crack grows, that carries more. But as that crack continues to go, actually the stress concentration decreases. And that's because the composite is carrying more stress. So we matched the Young's modulus of the composite to really optimize that. And, we've looked at, so this is just this is something where we're looking at our change in the electrical properties of the sensor. And this is what we call the back face strain. It's actually, if you were noticing on this side, in the video, we get a compressive strain on the back. So we measure, it's actually a measure of our, is a measure of the length of the fatigue crack. And we see almost a perfect relationship between what's our back face strain and our sensor response. And actually, you see it starts to become nonlinear at some point. That's actually because we fatigue the strain gauge. So, but the sensor continued to work. Of course, you can't put a back face strain on a bridge, right? But so we were able to take this, and we showed this very uniform, very repeatable ability to sense. This is a number of cycles to failure and our change in our electrical properties, and we know that that's quite linear with the crack length. This is the fatigue life. This is where we drilled a crack stop hole. Only increased it about less than 10%, right, in terms of fatigue life. But when we add our composite repair, we're getting around 400% change. So a very significant change in the fatigue life. And this was where it was fun. I got to be a civil engineer for a day. So we went out on the bridge and actually installed this sensor. This is in Wilmington, Delaware. And what you see is I'm safely on land taking pictures, but this is over a river that's downtown Wilmington. So there's, and background is the Joe Biden Jr. train station. And we were even kicked off the bridge. There was a tall ship. It's a drawbridge, but this has quite a few fatigue cracks. There's where you see the actual sensor, and these sensors are fairly small. And it has the structural repair integrated. So we could just go out, stick it on the bridge. And then we had to add our data acquisition, and we send that, and you can see those are the students. This is where the fatigue crack that we were monitoring, and we have a little data acquisition system, and we're able to send that over the cellular network. And the idea here, we were taking data and also taking data locally so we could do the analysis. And writing it to an SD card. But ultimately, this could be a solution where, we could be monitoring it all the time. And, if something happens, an event happens, a Dell dot engineer might get a text message. So it's just sort of a fun case study to show that we're able to do this. And as I mentioned, there's also one in Portland, Oregon. So in about the last 10 minutes or so, I want to talk about this, where we've extended this sensing to, from what I call from structural health to human health. And, I think I'm not wearing my Fitbit today, but a lot of, there's been a lot of pushing towards, having technology and wearable sensors. And, I think one of the things is that we're interested in, so say if you have an injury, right, and they might take you into the lab and do gait analysis, but if you, say, have a knee replacement or a broken a foot, one of the things that they do is if you go into a doctor's office, it's good to put some weight, as I understand, on the foot, but you don't want to put too much weight. And so the idea here is what they do is in practice, you go into the doctor's office, they have you stand on a bathroom scale, and once you reach that limit, they're like, okay, remember that. But the idea here was that we had actually developed these unique sensors. And this is just an example. So this is the same type of a sensor that's on the bridge. It's actually a non-woven fabric. We use an aramid fabric, but we can use a lot of different types of fabric. It's a non-woven fabric, and you can see those are the shoes I'm wearing today. And it slips right in to the insole. This is one of the first generations of our sensor. This is one of our undergraduate interns walking in the grad office at Delaware. And you can see as they walk. So it's kind of the idea is that would be a quantitative Fitbit, right? And what's unique about this sensor is it has an extremely wide sensing range, a really wide dynamic range. I call it from touch to tons. It's because of the mechanism on how the sensor works. And we've done a lot of studies looking and understanding how this sensor is. But this is just an example where we're just ramping up the pressure. This is from very low pressure to very high pressure. And the resistance change actually is nonlinear, but that's actually what gives us our really wide sensing range. And we can calibrate that and do a curve fit on that. And as I mentioned, this sensing mechanism is we compress where the fibers actually in the, this is just a cartoon of how we're compressing the fibers touch, but then we're also compressing that foam-like interface, and that's changing the electrical conductivity. And so literally when we did this, it's literally from touch to tons. So this is the example, for finger pressure, standing on it, like if it's the foot sensor in your shoe, but we drove over it with the forklift in the manufacturing lab. And there's really is no damage to the sensor. So it's literally from touch to tons. And as that sensing mechanism, as I mentioned, you're compressing that, kind of foam-like interface, but also what happens, and why we use the aramid fabric, is that the transverse strength is fairly low in the transverse to the fiber direction. So that causes actually the fibers to flatten out a little bit. So if we're using it for a very high pressure sensor, what we do is we have to preload it up to that sensor because there's a little bit of change because of flattening it out, but it's really that mechanism which gives us this huge range. This is just another couple of micrographs, again, showing the non-woven structure, but also showing these many different contact points, which is the essence of the sensor. And it's very, very durable because it's bonded onto the surface. This is where we use some commercial nanotube dispersions and then just sort of coated it, and you can see that peels right off. So it's made it a very durable sensor. And then, of course, this is where we started getting into, this idea of, and this was actually a senior design project in another lab where they developed this smart boot. And I actually, I read about it, believe it or not, I read about it in the Philadelphia Inquirer, but my friend's office is just down the hallway. But they developed this smart boot. As I mentioned, it was like your quantitative Fitbit. You don't want to put too much on it. So the first generation would go from red to green. The current generation has our sensors in it. And we're doing a lot of human subject tests. And we did this validate, if you go into a laboratory for rehabilitation, this is my colleague, Jill Higginson. This is her lab. She has all kinds of fancy motion capture. And this is an instrumented treadmill with a force plate. So we did to validate it, but you can only do that in the lab. And one thing is that when we have human subjects that come to the lab, they know they're being watched, right? So they may change how they walk. But the idea is to take this out of the lab so that you could walk around, you could walk up and down stairs, you could walk on grass, and you'll be able to monitor that. And maybe at the end of the day, you can pull your phone out and see how many steps you're in range or how many steps too high. So we validated this on the treadmill in the lab with a very sensitive force plate. And you can see there's quite a bit of, from the treadmill and the sensor, it's quite accurate. It tends to be a little bit less accurate when you're walking fast, and it's partly because we're not taking data. They're taking data at something like well over 1,000 hertz on this treadmill, and we're not taking it. So sometimes we miss that peak. But this is the validation. So this is what's often referred to in biomedicals as the M curve. That's the response of the treadmill. Here is where we have a sensor in the ball and heel of the foot. But now we can take that. This is walking upstairs. So now you can see how you've changed that weight on your foot. So we have a new project looking at that. We just published this recently in Wearable Technologies. But the really cool thing is that, well, now we could, have these sensors, but we can also have a wearable sensor in a garment, because this enabled by the coating process, we can coat a lot of different types of fibers. So this is an example. So what we're thinking, and this new project is addressing is virtual therapy, right? Especially during the pandemic, all physical therapy and everything moved online. And how do you measure the range of motion from a Zoom call, right? So, but these could be some sort of a sensor that you could wear. And then that could go to the physical therapist. I know when I was in a car accident and I had physical therapy, I sometimes cheated on my exercises. So that this would be kind of a way that you could almost make it like a game. You know, do your exercises, get a trophy, right? And this is actually this virtual reality fitness game that I play. And so that's the idea is for virtual health. But what's remarkable is the sensor sensitivity. So this is a knitted fabric. It's just some fabric that we went to the, you know, I think it was Joann's or whatever, and just bought some fabric off the shelf. And it's a knitted fabric, it's a weft knit, and it's polyester. But what you can see is extraordinarily sensitive. So, and in fact, if I, you know, go from full extension to about 90 degrees, that changes 3,000%. And so this is a wearable garment, and this sensor, you wouldn't know that there's any coating. It's soft to the touch, it's breathable, and highly sensitive. It's actually that mechanism, it's a mechanism of deformation of the unit cell of the fabric that gives rise to a really high resistance. And we've, of course, also done this on a knee sensor. This is where we have our human subject stand. And as I mentioned, this is this mechanism of how the unit cell deforms, and it's actually it's biaxial stretching, which gives us this really large range. But that really high sensitivity, we can use it for a lot of other things. So this is just an example of where they're wearing it on the forearm, and just that fairly delicate motion, we have a very large change in our electrical signal. And that's also the advantage is that these are so sensitive, it's very low power. So you can charge up at the beginning of the day and wear it all day. This is showing it can measure delicate motion. So the idea here is that here gripping different radius curvature items, and that we see still a very, very large change up to over 1,000% change in the electrical conductivity or resistivity in this case. You can see that response just to that very delicate motion. And so this is our idea to take it out of the lab. And we have a new project where hopefully we're going to be doing a lot more validation with human subjects. And hopefully, as I mentioned, so this again, you wouldn't know this is wearing this as an example of actually the gait analysis, and you see all the markers and other sensors that this person is equipped with. And this is just our sensor, and we've miniaturized our data acquisition, so it has a Bluetooth shield in it, so it can send it directly to your phone or to your laptop so that we can acquire that data and study the data. And it's smaller than this one is just our first one, but it's smaller than a credit card, and it can certainly be miniaturized further. And then this is just an example I thought was very fun. We actually 3D printed this hand because we wanted to be able to measure, have a repeatable way of, looking at the sensor response and the durability over time. But what was fun, they decided that, well, we're going to put the finger sleeve on and actually use that to control the hand. I think maybe, possible ideas is that could be human-machine interaction. But I guess just before I conclude is it's really been enabled by this coding process, and we've studied and understand the chemistry. We developed it, we patented the process actually, and created a startup company also to look at potential commercialization. One of my PhD students did that. So just in conclusion, so really this scalable manufacturing is this enabling technology. And, by understanding the science of the deposition process, that opens up the door to a lot of these different fun application areas. We can measure this in real time, and it can be a quantitative measure of things like pressure or damage in a structure, but also, now perhaps for human health. And these fabric-based sensors, they really show a wide range wide dynamic range, and that's by that we've been able to study the mechanism by which these sensors work, and also because we can control the process, we can try to optimize that sensor response for different applications. And then, as I mentioned, we've been doing this analysis of human motion, and we've also done the structural monitoring, which is really from that. So I guess with that, I just want to acknowledge it, is all the students and postdocs who have worked on this over the years. The student, Sagar Doshi, is currently a scientist at our Composites Center. He really led a lot of the applications and created a startup, but I've been fortunate to work with some of my civil engineering colleagues and also the biomechanics and movement science. I did my sabbatical in Australia, and Andrew Ryder at the DST group, we did quite a bit of our fundamental studies of looking at the fiber and fabric surface. So, of course, all the funding agencies. So with that, hopefully we're on time. So. I don't see a clock. So. And with that, I'd be happy to answer any questions. Sorry. Could you speak up a little?
Yeah. Thanks for the interesting talk.
Yep.
So I got a question about the resolution of this sensor. For example, for the fatigue crack, what is the smallest crack you can detect? For the human motion, what is the smallest pressure you can detect?
Yeah, so for, that's a good question. So for the structural health monitoring, for the fatigue crack growth, we can sense that in, I guess we don't think of it so much as in the resolution, but, as we do these tests, they're over time, but is that we can certainly sense as that fatigue crack is growing. So certainly less than a millimeter. I think the resolution of the sensor is partly dictated by how tight our mesh is. We can do different aerial, and we've studied different weights of the fabric to try to optimize that. But a lot of that was, unless you fracture, because what actually happens is that the fibers don't fracture, but you strip the coating off. So for the pressure sensors and some of these other sensors, we can just measure, literally in the tactile range, and then it's highly repeatable. We've done, multiple cyclic loadings, several thousand cycles, and it's highly repeatable, both from very low pressure range, and we chose that based on tactile pressure, but also up to quite high pressure. And we're doing a lot of work also looking at the durability of these sensors. So we've done a lot of studies of environmental, changes if you sweat on the sensor, and that's something that's ongoing. So, but they're quite reliable. We've had a number of these sensors. We've been using them for quite a long time. So yeah.
You mentioned environmental testing, and
yeah.
I wanted to ask, how long was the sensor deployed on the bridge, and what kind of environmental extremes did it have?
Yes. So on the bridge, we had that sensor where it's actually still on the bridge, but we're not monitoring it anymore because the project ended, but that was on there, when we monitored it for about 1.5 years. And then we've done a lot of environmental studies. I have a paper, I didn't talk about it today, but on both the thermal as well as the moisture, particularly for the structural sensor. We're currently, for the garment-based sensors, we washed them many times. I bought a washing machine for the lab, so we could do that. And those are very, very durable. And I think one of the things, there is a component where it's a little sensitive to moisture in terms of the sensing response, so if it's wet. But because the sensor has such extremely large electrical resistance change, that is what dominates. So that change in the electrical properties due to the moisture is small in comparison.
A couple of
question. First of all, what is the volume fraction of your carbon nanotube versus the
So the volume fraction for which, if it's on a,
as you call substrate? I mean, you basically deposit
yes,
the nanotube on the fiber.
yeah.
My question is, how many?
Yeah, so I mean, what we really look at is change in the areal weight, and that's related to the coating thickness. But for example, when we do these depositions, we create, a few liters of our solution, and we're making gram per liter, sometimes 2 gram per liter, so very dilute dispersions. But we use those dispersions for many, many, many depositions. So the actual weight change of the fabric, in terms, I don't have the data with me right now, but the actual weight change were just fractions of a milligram, because that coating is so thin. And of course, that depends, it partly depends on, and that affects how the process works. It partly depends on what the microstructure of your fabric is. So when we're doing the sensing work, we're depositing just a very thin coating, and what we want to do is coat every single sensor. I didn't talk a lot about the mechanical property change, but what we want to do is we want to get a much higher volume fraction. So we can get nanotube volume fractions in a fiber composite, typically in about, I guess we measure weight percent, but converting just volume fraction, we can get about 10% nanotube volume fraction in a fiber composite. So that's replacing the matrix. So the fiber volume fraction is typically around 55% in the way we're manufacturing those composites.
How did you disperse all those nanotubes? Is it a big effort?
Yeah, so for the nanotubes, what we do is we develop this process where we use ozone gas and ultrasonic. So we use ozone gas, oxidizes the surface of the tubes, and that provides a chemical group because there's very low oxygen on the nanotubes themselves, and we just buy these tubes. And the question I always used to get was, oh, tubes are so expensive, right? But now we can buy these for just a couple of dollars a gram, and we're maybe making our dispersions using a couple of grams. So I guess chemical functionality, what we do is we oxidize the surface, and then we graft the polyethylene amine molecules onto the surface. So it's a continuous, we sonicate and ozone treat, and it depends on the oxidation rate and how much we're bubbling in, but we do that for about 10 to 12 hours, and then that provides the site where we can bond the PEI onto, and that doesn't take too terribly long. Yep.
Have you tried this for a composite structure in terms of?
Oh, I'm sorry. Say
have
it.
you deployed this technology to a composite structure, the repair and the monitoring?
Oh, for
Composite. You use composite for repairing, right?
yeah. So for this project that I talked about, we're using the composite as a repair. So we're not monitoring the composite, but we're monitoring the fatigue crack.
So have you tried for a composite structure? So you're using composites for repair on a steel stamp, for a steel structure. Have you tried that for a composite structure?
Yeah. So I mean, we've done. In fact, I tried to. I could spend hours talking about our work, but we started our work doing structural health monitoring of composites. So we've done a lot of work where we have looked at repair and being able to monitor, in a composite structure that's been damaged, monitoring the repair. We had a project actually that was funded by Aerospace manufacturer, specifically looking at that. We've started this work under Air Force program where we use it to sense cracks in the composite, and partly is that the cracks that form in composites are very hard to detect. I think that's part of the reason that fatigue life of composites is very uncertain, because these microcracks form, and it's very sensitive. Our initial work showed we were quite sensitive at being able to detect those cracks.
So looking at the sensors now, what's the effect of moisture, considering that composites absorb moisture over there?
What is the
Effect of moisture absorption?
Oh, moisture. Yeah. So as I mentioned, so when we on the bridge, basically what we would do is we monitored the humidity, and we've done a lot of work where we characterized and looked at this in the. We had a Navy project actually where we did seawater immersion of these, and there is a change, and it's actually not as much as we had thought it might be. Due to the seawater immersion or ambient moisture, is that the sensor itself is quite sensor is sensitive enough that the moisture component is small. There is and I didn't show much of this data, but there's a thermoresistive component. And that thermoresistive component, so is basically as you heat it up, the electrical properties will change, right? And so what we do is in the field, and we've done, and we understand the thermoresistive behavior, but in the field we compensate for that. So we have a temperature sensor on there, and it's even for a traditional strain gauge, you have to do temperature compensation. So there's a component of that as well. But that's from a very practical point of view, that's an important topic.
So, due to time, let's get one more question.
I definitely want to say this is one of the great talk. We're able to, from the bottom up approach from nano, and then scale up this to the real applications.
That's where it's been a lot of fun, is that, is like being able to take it and studying the chemistry in the lab, and then now being able to put it on people and bridges. And
so now my last question is that when you say the sensitivity of this sensor, when you compare with regular strain gauge, what is your gauge factor?
Oh, sure, yeah. It's much more sensitive, but the gauge factor. So that's how we, if you look at a strain gauge, you can almost predict exactly based on axial strain and Poisson contraction of copper what the resistance change is, and that usually gives you a gauge factor a little under 2. And so for these, we might have gauge factors. It depends on a lot of effects, but we might have gauge factors well over 1,000. And for the fabric-based sensors, I guess we haven't specifically done a lot of strain measurements on those fabric-based sensors, but you can see that those are certainly sensitive. But the piezoresistivity is always higher, but that depends on a lot of factors like nanotube volume fraction. And then actually what happens is that the sensors, so we talk about electrical percolation, and that's where you create the conducting network. And these sensors actually become more sensitive as you get closer to that percolation threshold. If you have too many electrical connectors, there's too many conductors. And so it becomes, the gauge factor drops, it might just be, it's higher than a strain gauge, but it might just be in, 3 or 4. But so certainly for others, it's over 1,000. So, and that's something we can control a little.
Okay. So as we conclude, let's express our thanks again.
Thank you so much for the invitation. I appreciate it.
Thank you. It's behind the screen actually, so let's raise the screen. Yeah.
So do we need to stop?
Stop and then.